Hi, in this video we're going to continue our discussion of 14.6, discussing what's known as the gradient. Now the gradient might be a word you're familiar with from general English vocabulary. We're going to try to get the notion of slope really pinned down for any kind of function, ideally. Even for functions where it's more than 3 dimensions, and again by that I mean maybe 3 inputs, 1 output, a 4-dimensional function, or even just to hone down finally what we really mean by the slope of a surface. Is there a way to get a nice notion that we could use for almost everything we want? And it turns out there is. So we start with the directional derivative we were talking about in the previous video. The directional derivative of f in a specific unit vector. So u equals a unit vector u1 and u2. And f of xy is any function or surface. Well, any function, I guess. 3D function, which is making a surface, okay? It takes 2 inputs, outputs one thing. It makes a 3D surface, like a sheet. This, at any x, y point, it turned out we were going to use the partial derivative with respect to x times u1 plus the partial derivative with respect to y times u2. Okay. Now, a useful fact is to notice that this decomposes into a dot product. This composes into the dot product, fx, fy of the partial derivative components dot with the unit vector itself. And I am using now, I know I use dots over there too. This is the dot product. And what is a dot product of? This is just our u hat. And what might this be, right? This is a big question mark. This is a weird vector. Who knows what it's representing? Like, why would you just arbitrarily stick them together, except that, wow, it just works to make this interesting little video here? Well, the reason we stick them together is this guy is not some random weirdo vector. This guy is one of the most important vectors we can define in this class. This is called the gradient vector, or just the gradient often. It's one of the most important vectors in all of calculus. It will have its own symbol, an upside down triangle called a nabla. And we're going to write it as, when you see that symbol, you take the 2 components as the partial derivative with respect to x and the partial derivative with respect to y. In I hat, j hat notation, it's fx in the I hat direction, fy in the j hat direction. It should make sense, right? The j direction is the y direction. The I direction is the x direction. Now, why do we care about this? Why do we care about this at all? Well, for one, it lets us write this, neat looking formula. And I mean neat in a very literal sense here, just neat looking. The directional derivative is just this notion. Is the gradient vector dot product the unit vector you wanted. So any directional derivative we want to find will just be a dot product. Okay, and I want to be really clear here. This is connecting 2 key ideas. I've been emphasizing for a few days now, this is a scalar. One of the reasons it's a scalar is because it's equal to a dot product. The other reason it's a scalar, just to be fully clear about this, is because it's supposed to be a notion of the change. This is a scalar, a slope, right? It's a notion of change, or a scalar. A scalar rate of change measurement. Okay? Of f, of how f's z coordinate changes in the u direction, if you wanted to spell it out fully, of how f's z component changes in the direction of u at a specific point. Whereas the gradient of f is a vector. Okay, it's part of the directional component, but what this is going to be one of the major keystone parts of this class, or specifically of vector calculus, chapter 16 material. What does it do? So here's where you might have seen this from, your normal day-to-day English language. It relates the grade or the climb, or maybe a general notion of steepness of the surface. Sorry, we can do that this way, of the surface. It's a general measure, okay? It's a general measurement of the steepness. Okay. It has a very, very useful notion in terms of potential energy that we can start to talk about on the next slide. If I roll a ball down a hill, what path will the ball take? Okay. Other things being equal, it will take the path that lowers its potential energy the quickest. That's one way of understanding physics. If I wanted to lower my potential energy quickest, I would want to go down the hill as fast as possible, right? This is the idea we're kind of talking about hill. We want to make sure we can figure out at each point on the surface which direction would maximize my change, so to speak. That's why it's such a useful idea. I'm going to get into that in a second. We're going to define that in a really clear second. But for a specific slope, obviously we will still need to know the direction you want to move from a point you're on. And for a specific grade, we'd have to know the exact point. Just putting these two partial derivatives together, just putting these two together in a vector might not tell us too much without defining a lot of what I just was talking about fastest change. But if we start putting this together with coordinates x, y, and with unit vectors, then we could talk about an actual slope from a point, blah, blah, blah. Okay. Let's define some properties here of the gradient f. Okay. On that last slide, I was noticing that nabla was really big. It doesn't have to be ginormous. I hope that really didn't mess you up. I just was excited about it. So 1. If the gradient of f equals the 0 vector, then duff, the directional vector, is 0. Notice this is a scalar, this is a vector. I'm not forgetting a hat. Is 0 for any or all directions. That's one very powerful idea. If you find out that your gradient is 0, this is going to help us get back our notion of critical numbers, of relative max and mins, that at a point where the gradient equals 0, all of the slopes, all of the possible tangent lines you could draw would have a slope of 0. Meaning we are locally, horizontal tangent plane, let's say. We have a tangent plane that's parallel to the xy plane. That's going to be what it's saying. A flat. The tangent plane is parallel to the xy plane. That's what we're saying. Okay, getting that kind of notion back is helpful. And one of the ways to find it is just by setting both partial derivatives equal to 0. 2. The max value of the directional derivative is the magnitude of the gradient. Okay, that says the magnitude of the gradient, not the absolute value. When the bars are around a vector, we're talking about the magnitude. This happens, still on the second bullet point, when the unit vector is parallel to the gradient vector. I don't just mean parallel, I mean actually the same exact direction, okay? Not counting anti-parallel. To go back to that, we're going to do a quick little proof of this. It's not actually terribly hard, but since the direction vector is a dot product of f with a unit vector, dot product, if you recall, can be translated into a magnitude discussion. The magnitude of the magnitude of the gradient times the magnitude of the unit vector times the cosine of the angle between them. Okay, now, since u is a unit vector, the magnitude of u equals 1. So I can get rid of that pesky thing. And we're just talking about the size. The directional derivative is just the magnitude of the gradient times some value of cosine. Cosine of whatever the angle was of the direction we were taking in the xy plane. This is maximized when what happens? When theta equals 0. And then the directional derivative would just be, okay? And then 3, it's sort of the same thing, but just to put a fine point on it, the min value of this guy is opposite the negative version of that magnitude, and is achieved when theta equals pi, right? When they're pointing in opposite directions. When the, gradient is going one way and the unit vector is another way. Okay, that's what I'm talking about by theta here, just to be clear. One of the main things I'm trying to point out here is that any other theta gives cosine theta a value less than 1, right? So we'll decrease the overall size of the direction vector. The directional derivative of f at u. There are no in between. There's no way to get bigger because sine is trapped between 1 and -1. So then the magnitude of the direction vector is trapped between the maximum value, which is the absolute value of the gradient. The magnitude of the gradient and the minimum value, which is the opposite of the magnitude of the gradient. Blah. If we're getting bogged down in theory, let's try to if we're getting bogged down in theory, let's put a fine point on it. Okay. So, the gradient of f gives the vector, one more time, it's a vector where the steepest ascent or descent can occur. Gives the direction of the steepest tangent line at a given point. These are the same notion. Whoops, at a given point. Put it another way, if u is not parallel to the gradient, then u is turning our directional derivative away from the steepest climb. Which is the gradient. Again, don't think of it as climb necessarily. One notion that I think helps me understand, we're talking about, again, how the ball would naturally fall. To move the ball from its course, we will need some sort of force to act on the ball. Okay, one more picture, I guess. So there's my surface, there's my point again. The gradient at that point would be the steepest tangent line I could draw there. Okay, and to move the direction, it's like the so this is the gradient. That's the gradient of f at that point. And when I move my direction of travel, if I try to alter off the gradient, all I'm getting is a less steep tangent line. It's definitely hard to draw this as best as I can, but again, just try to picture that situation. This hill is really flat if I walk along the x direction. Maybe it's flat if I walk along the y direction, but it's not flat in this one direction. There's a valley running through. We'll also notice that the gradient of f has one fewer dimension than f. Okay, f is a 3D surface in this case. The gradient of f lives in the plane. Okay, right? If f of x, y, right, equals z, represents a 3D surface, the gradient of f is only a 2-component vector. So it's always going to be a 2D vector. Then the gradient of f is a 2D vector. And this is going to end up being true in higher dimensions as well. That's another really important use of it. Right. Enough theory, I'm sure. Let's just get into some computations. So, find the gradient of f of xy given f of xy is 1 over x squared plus y squared at the point 1, 2. Okay, so this kind of question is really no big deal. The gradient of f is the vector x the x component of the partial derivative, the x partial derivative, plus the y partial derivative, and just put into a vector form. So on your paper right now, pause the video and try to find our two partial derivatives. Pause the video now. 3, 2, 1. You should have gotten a pretty symmetric looking idea. Negative 2x over x squared plus y squared, quantity squared, for f sub x, and for f sub y, the same thing, just with the y's. So my gradient of f is this whole thing in the I direction, plus or minus, it really doesn't matter, 2y over x squared plus y squared, quantity squared, in the j direction. What is this represent? What does that represent? What is this representing? Maybe is what I was trying to say. This vector right here is the vector for max slope at given point, at given xy location. So when I plug this in, when I actually evaluate the gradient at 1, 2, and get negative 4 over, what are we talking about, 5, 25, minus 4 over 25 in the j hat direction, that is the direction I would walk on this curve at 1, 2 in order to achieve the greatest rate of change, in order to achieve the greatest change in my height per time, per effort, right? If I wanted to move the least and get the most elevation change, that's the direction I would go. Negative 4 over 25ths in the I direction and 4 over 25 in the j direction. Okay, I think this video is getting a little long. In the next video, we'll talk about three-dimensional gradients. It'll work very much the same way. I hope this was understandable. See you in the next video. Thanks for your hard work.